my dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel. I'd like to welcome you all to our International Physics webinar. So good evening all here in Bangladesh, and a very good morning to all those who are watching this program live from USA. So hope you are well and safe from Corona pandemic. As we know that the Corona pandemic, we are staying in a Corona pandemic situation since 2020, but the situation now becoming worse. So we have to follow the health rule. So we are trying to adjust with this new normal situation. As we cannot continue our normal academic program inside the campus, we have to start our online program. So I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has already started its online program, including online international physics webinar. And we have already successfully completed our 141st international physics webinar, including 2 Nobel laureate speakers. And today it's our 142nd international physics webinar. So today I'd like to welcome you all to a joint session between our department, Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, University of Nebraska-Lincoln, USA in Physics and Astronomy. And we have with us here today Dr. Herman Batelaan, Professor, Department of Physics and Astronomy, University of Nebraska-Lincoln, USA. And he has already connected with us through online. So I'd like to welcome our speaker. Sir, good morning and good evening to here.
Yeah,
Thanks
good morning.
for our invitation, sir. So we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. So we have organized this international physics webinar in this Corona pandemic situation to motivate and encourage our students. So we are trying. I think our students are benefited by this program. So for those who are new, I'd like to inform that we have divided our webinar into 3 parts. First of all, we'd like to introduce our speaker with all of you, and then our speaker will deliver his speech. And at the end, we have a discussion session. In that time, anybody can join with us. So I think you have already come to know the title of this today's International Physics webinar. Title is Quantum Mysteries Revisited. Very interesting topics. And our speaker is Dr. Herman Batelaan, Professor, Department of Physics and Astronomy, University of Nebraska-Lincoln, USA. We can see his academic and professional career. Dr. Herman Batelaan studied his physics at the University of Leiden and obtained the PhD at the University of Utrecht. After temporary position at the State University of New York at Stony Brook, University at Innsbruck, University of Nebraska, and the Technical University at Eddington. He became a professor of the University of Nebraska. He is a fellow of the American Physical Society for outstanding contribution to electron matter optics, in particular the measurements of Kapitza-Dirac effect and elucidation of the Aharonov-Bohm effect. You can see his educational and professional record. He completed his master's University of Leiden and PhD University of Utrecht, Netherlands, and postdoc fellow quantum electronics group SUNY at Stony Brook, NY. Lies Meitner fellow 1994 to 1996 Institute for Experimental Physics, University of Innsbruck, Austria, and research assistant professor, lecturer 1996 to 1990 Atomic Physics Group, University of Nebraska-Lincoln, and research associate 1998 to 1999 Atomic and Optical Interaction Groups, Technical University of Eindhoven, the Netherlands, and assistant professor 1999 to 2003 University of Nebraska-Lincoln, and associate professor with tenure 2003 to 2010 University of Nebraska, and visiting professor in 2005 September to November University of Innsbruck, full professor 2010 to present University of Nebraska. Research, their group studied the fundamental interaction between light, electrons, and atoms. Their interest focus on studying the foundation of quantum mechanics and electromagnetic interaction. These studies include the theoretical analysis, simulation using supercomputing, ACC, and XSEDE, and the strong emphasis on experiment. Awards and honors: Fellow of the American Physical Society 2009, citation for outstanding contribution to electron matter optics, in particular the measurements of a Kapitsa-Dirac experiment and the elucidation of the Aharonov-Bohm effect. Sigma 11, University of Nebraska Chapter, Outstanding Young Scientist Award 2003, Certificate of Recognition for Contribution to Student Teaching Council of the University of Nebraska 2000, 2001, 2011, 12, and 14. This is his collaboration and other affiliation, and this is his publication. So thanks all of your patience. Now it's time to go to our speaker. Sir, welcome to our webinar again. So it's your time, sir. You can start your session.
Okay, I'll start sharing my screen. So
yeah, you
first
can.
of all, thank you very much for the wonderful invitation. And
it's our honor and privilege to host you in our international physics service.
Yeah, it's wonderful initiative that you're taking, and I'm happy to help out with trying to reach out to students. Okay, so I'll share my screen. And,
not yet, sir. You can.
Not yet?
Yeah, not yet. You can share.
I'm sorry.
We can't see the screen.
Yeah, okay. I'll start clicking now on the sharing of the screen. So give me a second. Okay, and I hope.
Yeah, we can see.
Do you see my screen?
Yes.
Yes. Good. All right, then let's get started. So again, thank you for the invitation. It's really really lovely. So here's the map of the places I've been. On the list was not that I was also a guest lecturer for a couple of weeks in China, which I really enjoyed tremendously too. So it's been a pleasure to be a physicist and enjoy doing what I love to do most. So that's really fun. I would also like to show here pictures of people that were in my group here in Nebraska that got the PhD. The year here when they got their PhD is in there, and of course without these people I could not have done any of the research that I did. So to them, of course, a great thank you. Here are some other highlights of things that I find enjoyable to work on in my life. And you may notice from these title that, the Stern-Gerlach effect, we did something there where we showed that Bohr and Pauli made a mistake, which was kind of neat. We did something showing no force in iron Bohm effect, which is one of these things you can find in standard quantum mechanics books. And today I talk about the electron double slit and Kapitsa-Dirac. So I really like basic foundational quantum mechanics. And the work has been funded by multiple agencies, mostly by National Science Foundation continuously from the year 2000 till now, which I'm of course delighted with. So let's start. Let's start with something we all know. This is a picture that came from the Feynman Lectures of Physics, so it's directly copied. And he shows us an electron gun that sprays electrons from the left to the right. By the way, can you see my mouse?
Yes, sir, we can see.
All right, great. So electrons come from the left. They move to double slit, and we have a detector that we can slide. If we block slit 2 and we slide this detector, we get a distribution P1. And if we block the other one, we get a distribution P2. And if we open both, we get here an interference pattern. We all know and love this, I hope. And this is an addition that we made to it. So we built the machine. I'll show a picture in a second. But we put a little mask in there that we can slide. So if this mask moves and blocks slit 1, one can take an image. Here it is. If you slide it up, you block 2 and 1 is open and you get an image. And if both are open, we get this image. So indeed, we did this experiment, and that was prompted by the outreach manager of the Perimeter Institute of Theoretical Physics in Canada, who wanted to make a movie for high school students. So that's why we actually did this work. Now, I want to show a movie. So the left movie, let's see if it will go. I hope. There we go. Here's the slit. It moves, and then the first slit opens, and then we see, so these are real images, not simulations, it's data, the blob of one slit. As soon as the second opens, you see the double slit appear, the double slit interference pattern appear. And as soon as here the next one starts to block, we have a single slit diffraction pattern. And the slit separation is about 300 nanometers. The slits themselves are about 100 nanometer wide. So you have to make this at a small scale to be able to do this. And the mask has to be in the near field, which is in a few microns, to be able to do it without breaking these membranes. These are very thin 100 nanometer membranes that in an iron mill, you cut the 100 nanometer slits, you coat them. And so to put it together, you can imagine it took about 1.5 years to learn how to do that, because the things tend to break easily. Here's another picture and movie, and it's slow. There's not much. Here's a little dot. There's the first one, second one, third one. So we recorded here a diffraction pattern, 1 electron at a time, real time. Now, of course, we can sit here forever, but if you just wait a couple of hours, then we'll have seen the pattern. Now, we're not going to do that. We're going to, of course, speed up not the emission of how many electrons are emitted, but simply the play time we just speed up. But this was really recorded 1 electron at a time, and that's kind of important. I'll come to that in a second. So what we often see in a teaching room is you have maybe a water ripple tank where people shake at 2 sources and you get a double slit diffraction pattern, or maybe 2 sound speakers, and you pick up the sound and you might move your head from left to right and hear the maxima minima of the sound. Now, of course, electrons and matter are not like that. The entire point of this type of experiment, which the first one I saw was from Akira Tonomura, that was for a biprism, not for a double slit, but still it got the idea very nicely across, is that in the machine at any one time, there's only 1 electron there. Now imagine you would do that with sound. Imagine you have an instructor has 2 speakers of sound, and then he turns them on and asks you, oh, move your head. Now you can hear, oh, there's a maximum, minimum, etc. I say, oh, that's nice. But imagine the instructor would remove all the air molecules in which the sound wave propagates. So you have 1 air molecule left. Well, that's a problem. Of course, we wouldn't just not hear the interference pattern. We would suffocate because there's no air, which is terrible. On the other hand, for electrons, if you have 1 electron at a time, you still see the diffraction pattern emerge. So, for high school students or people haven't seen it yet, and you say, okay, in sound waves, the wave is made up of, the medium is made out of the air. And molecules bump into the next molecules to propagate the wave. Of course, for electrons, that's not the case, right? The electrons do not have to bump into other electrons to set up the wave. That's what this is for, to bring this, to the forefront. And this was used in more than 100,000 high schools as a teaching material. This is kind of nice. And the Permanent Institute of Theoretical Physics brought this out as resources for that purpose. Also, there is a lot of historical work, and I should mention Klaus Johnson and Pottsy, who did, pioneering work before me in this for this type of experiment. Nevertheless, we were kind of happy to do this because, I should also mention that Roger Buck is a grad student who did this work. He came originally from a farm in Kansas, and from that background, he worked in the group on this experiment. It was lovely to work with him. Now, Feynman said, we should say right away that you should not try to set up this experiment. This experiment has never been done in just that way, while this was in the 60s. The trouble is that the apparatus would have to be made on an impossibly small scale to show the effect we're interested in. And he meant this experiment. So we have done it, and this is published in 2013. And I was surprised that nobody did it exactly this way. And so that was, it was very nice to do. Now, let me bring you back, though, to that first electron. I mentioned on that screen that the first electron landed there. That was, of course, coincidence. But the thing is, it came in so slow that you can stop the experiment there. All right? So you can do that. So let me look at this thing and say I've stopped the experiment. And I've actually sat in my lab, looked at the screen. The screen that we're viewed this in is only 2 centimeters big. And we have a camera, and so you have a little bit expanded view. But I sit there, and you see, you can actually see by eye the fluorescence of the screen where an electron has hit. And then you can turn off in that second the source, and it stopped. So they have a completed experiment. Now let me ask about this experiment where one electron is detected. Is momentum conserved? Now, had we been in a room with actual people there, I would actually try to start a discussion. I've done this many times in talks, and it would be fun. And with this medium, I think that's hard to do. So, but it's interesting that when you listen to professors, postdocs, students, graduate students, undergrad students, it's funny when they have not really seen it. Then they say, oh, I think that momentum is not conserved because Heisenberg uncertainty principle allows to do so. Or no, momentum conservation is a fundamental principle. You can never do that. And people seem to be divided when they just are put on the spot to answer the question. Now, if momentum is conserved, something else got to take away the momentum. And it seems pretty likely that it's degrading because that's what the electron it gets close to and interacts with. So is this what happens? Now, we can go back to the history and go back to the Solvay conferences in the Einstein-Bohr dialogue and say Einstein measured the recoil of the first collimating slit here. So this collimates the beam. And then you get diffraction from this first slit, so the electron go up or down, and then set up an interference pattern. But Einstein said, if I have this set up, then, without disturbing it, I could measure the recoil of the slit, know through which way the particle went, like this. If you get a recoil down, then the electron went here, but I didn't disturb it, so I still must see the interference pattern. Or you could have this, right? The recoil goes up and the electron goes there. And he said, hey, I can determine which way the electron goes and still have the interference pattern, and quantum mechanics tells me that it's not the case, so the theory must be incomplete. Of course, Bohr, who was defended in this case quantum mechanics, had the answer. They said, yeah, well, hang on. The Heisenberg uncertainty principle protects quantum mechanics, because you have to know the position to know where the electron goes, like this. Say that the recoil is up and the electron goes down, then if the slit was here, the recoil could be up, but you go to the upper slit. So you have to know the position of this better than the separation. And if you calculate, and you have to know the momentum well enough to see this kick. So you have to know the position and the momentum well enough to do what Einstein proposed. And what happens is that is a condition that would violate the Heisenberg uncertainty principle, and thus quantum mechanics indeed protect itself. And Einstein's argument did not work there, which is, of course, famously documented in these Solvay conferences. But what we learn from that is this. Both assumed momentum exchange between the electron and the slit, right? There's momentum exchange there. So both assume momentum conservation. So the answer is there momentum conservation? The answer is yes. Now, Wouters and Zurich, so that's a famous analysis decades later, of course, assume the same thing, that indeed the slit and the electron exchange momentum. So when we have arrived at that point, then we can ask the question, what interaction caused the momentum exchange between the electron and grating? If we have established that this happens, what did this? Right? I mean, if you imagine the electron is a little mosquito and the grating or the double slit structure is like a bus, right? If the bus comes by and you see the mosquito move, then you know that the bus displays some air and the air pushed against the mosquito. What is it here? What interactions between the electron and the grating? And it's funny, I mean, the double slit is so fundamental. If you look at your textbooks, you will not find the answer. And that's surprising for something that's so pivotal. So I was a little bit, surprised by that. And I started digging into this. Now, when I did, got some results, I got invited talks, and I went to different universities, and I put this question in front of audiences. I did this at Harvard ITAM, at Texas Austin, Oklahoma, many places. And then I wrote down answers here from professors. And these are all very good professors. The second one, that professor asked, do you mind if I mention your name? But this was from Manfred Fink at Texas Austin. He was a delightful person to just, he enjoys just entertaining thoughts and ideas. So some people said electrons reflect from the Bohr edges. Well, yeah, maybe. That means, though, that if we would change the Bohr edges a little bit, that the diffraction pattern would change. And usually when we do experiments, if you do different coatings or different materials, the diffraction pattern stays the same. So this would be as a detailed answer are hard to maintain. Now, phonons are excited in the grading is interesting. So imagine that that the electron comes by, and by its electric field talks to maybe the things in the grading. That could, of course, be phonons or take it plasmons or whatever. And that could carry away the momentum. So maybe vacuum field photons, I mean, the vacuum field surrounds us all the time, we can't get rid of this, scatter the electrons, and the grading imposes boundary condition on that field. That's another answer that some people give, not one, but multiple. The electron's field acts on the grading, which back acts on the electron. That's kind of a more generalized thing that would cover certainly number 2. And then some people say this is a question one should not ask. Now, that if you have had a quantum mechanics course, you may have been confronted with that statement from a teacher. I know that I've taught quantum mechanics, graduate and undergraduate level quantum mechanics, and I have said this myself too. I've been guilty. And of course, it's not completely unreasonable, because if I use the words to describe quantum mechanics inappropriately, then maybe I asked a wrong question. Simply, just like in classical physics when we talk about work, right? Do I do work when I displace my phone like this? Well, the answer is no. But for the men in the street, you say, of course you do work, you get tired. So the things that we talk about in physics are very well defined. So we have to be very careful with the question. Is that a question one should ask? And of course, some students said, well, whatever idea you come up with, what about neutrons and photons? I mean, do we then have to come up with mechanisms for momentum exchange and diffraction for all of these things? Right? So let's focus on that question 5. And we should note that Feynman said no one has ever come up with a mechanism to explain the double slit diffraction, and nobody has till this date. So I want to compare double slit diffraction with something else that I did in my group. And what it did is, instead of a double slit, I took here a counter-propagating laser beam. So there's one laser beam coming from the left, one from the right, and that sets up a standing wave. Here is a green wave coming from the left and one from the right. And if you add them up, you get the blue wave. So you see here intensity, you see here no intensity, intensity, no intensity. So you have a periodic structure of light, a grading of light, from which electrons were predicted to diffract. That was predicted by Kapitsa and Dirac. Both later on got the Nobel Prize for some other work. But that was standing in 1933. And I decided at some point when I was assistant professor, this is an experiment I really want to do, because nobody ever succeeded in doing it. And I find this basic phenomenon just fascinating. Now, here's the setup. The setup is a vacuum system. This fits on one nice optical table. There's a laser back there, spits out 1 joule in 10 nanoseconds. And an electron beam comes from the back. There's tight collimation, so it's a very narrow electron beam. And then we fire a laser pulse. So there comes a laser pulse. Did that come across, by the way? Could you see that?
Yes.
Yes? Okay, great. Okay, thank you. So in this area, in the coherence length of the laser, it forms a standing wave, and the electrons see this, and they propagate towards the detector, and then you can detect here what happens. Now the data, now keep in mind, from here, from an empty table to getting the data took another 2.5 years. So here's the data. So if I look at this, this is the laser off, meaning if you scan here with a detector where the electrons are, you see a peak in the center. That's that peak. And we fit a curve to it. Then we propagate with quantum mechanics what happens if the laser beam is on. And then you get this black line and you predict peaks. Then you measure carefully and you see indeed those peaks occur. And that was the first time ever done. And we published it. And this was the grad student, Daniel Freeman, who actually with me in the lab did this. So that was a wonderful period of my life. And for the first time seeing this and sitting there in the lab, usually to measurement sessions that take till 2 a.m., 3 a.m. in the morning, because the laser has to warm up. Everything's got to be stable. Each data point here takes about half an hour measuring time to get it. So, then if things got unstable, you're going to start over. So it was exciting to see that data come out. It was really lovely. Now, when you look at this, of course, we can understand where these peaks are, right? This is this well-known expression, very well-known expression. D sine theta is n lambda d. So here's the first order, zero order, negative first order. Here's the angle theta. D is the periodicity of the light grating. And when you go to the first order, you make n equal to 1. If you have a small angle, we can replace d sine theta with d theta. And so we can easily get the angle theta. Now, from knowing the angle theta, we can stick that in the multiply it with the length. And then you get here the arc length, or the distance between the peaks. We stick in the numbers for this experiment, and we see that it is 55 micrometer. And then we look at what we measured, because you have a micrometer here, so you can carefully measure the distance. This peak indeed occurs at 55 micrometers. And since, quantum mechanic prediction works beautifully, you say, yes, we have seen this effect, and it's nice. Okay? Well, what was the purpose of this talk? I wanted to ask what interaction caused the momentum exchange between the electron and the grating, meaning the electron, say I would here stop again the experiment after one electron and it lands here. What did that here, right? What interaction caused the momentum exchange between the electron and the grating? Well, in this case, we know the answer. In this case, the answer is this. Let me do that again. So we start here, photon on the left, photon on the right. This photon travels to the right. This photon travels to the left. The electron moves through to the standing wave of light. And there come the photons, absorbed, stimulated emission. Again, so it comes, absorption, stimulated emission. So we start with a momentum of this photon with h bar k to the right, this h bar k to the left, so the momentum in the field is 0. Afterwards, both photons move to the right, and you've got 2h bar k to the right. So you go from 0 to 2h bar k, change in the momentum of the photon, which is transferred to the electron. So the electron gets a kick of 2h bar k. Now you might wonder, what angle is that then, right? What is this angle? Well, the angle is the change in momentum over the momentum, which is the change in momentum is the 2h bar k. I wrote here, so h bar k I can write also as h over lambda, or this is lambda optical. And we divide it by the momentum of the electron, mv. That's, of course, this thing in the triangle. Now, if you do that, then you rearrange h over mv here. You have lambda optical over 2 there. And what is that? This is lambda de Broglie of the electron. And this is the periodicity of the standing wave. Now, keep in mind, it's lambda over 2. A traveling wave has a wavelength lambda, but a standing wave has a wavelength lambda over 2. So this is exactly lambda over d, and it gives you exactly the right angle. So you have now 2 pictures. You could say the electron diffracts because you see a standing wave of light. It's a grating, and you use the diffraction formula. Or you could say, no, the electron gets a kick by the photons, by stimulated Compton scattering. That's why it gets kicked over. Now, of course, it could also kick over to the right if you first absorb from the left and then stimulate to the right. Or you do it twice, you can get the second order. So that's what diffraction is. And then you say, wow, we can answer the question, what interaction caused the momentum exchange between the electron and grating? Well, I think those people have said, which was about 50% of professors used to say, no, that's not an answer. It's not a question you should ask. That is kind of stopped now, because then they have to give a reason why here we can ask the question and we even can give the answer. I should mention, by the way, that this work was also inspired by the work of Dave Pritchard at MIT, who did atomic diffraction with standing wave of light in 1990 about. And I had the good fortune to interact with him, and he told me about this actually, that Kapistenorak proposed that first with free electrons and nobody had done it. So that was one of the important things that prompted me to do this work. So we go back to the double slit and ask the question, what interaction caused the momentum exchange between the electron and the grating, right? And I hope that you all feel, yeah, I would like to know now. That is a fair question to ask. Okay, so what could I, in principle, do if it's like Manfred Fink said, if it's a phonon that gets excited here? You could imagine putting this on a PZT, starting to shake this, right, and cause phonons to try to affect what's happening here. Whatever mechanism you come up with, you could imagine that you could test it. But of course, you also have to develop a theory to do so. And what is the status right now? The status is that this is a question that has not been answered yet by nobody on the planet. And for such a fundamental thing that we, you teach in high schools, you teach in undergraduate, or you go over it. Then in high schools, you talk about the phenomenology and where did the peaks go. In undergraduate physics, you maybe solve the Schrödinger equation. And we don't know the answer. It's completely unacceptable. That's my opinion. Anyway, we're working on it. Let's see, how am I doing in time? 9 o'clock, great. So I would say maybe, okay. So let me move to another question that has been answered that is much better known. So this is work that I do with Zilin Chen, and it builds on this double slit stuff. So again, I show here an animation from some other people of the double slit. So here's a double slit. You think of the wave function that you could find by solving the Schrödinger equation. You think of the interference stripes here in the back. And you think of the little clicks when in the traditional interpretation we would say the wave function collapses here at the detector. Now, there is this issue of the quantum measurement problem. There's many ways to describe this, but one way of stating what the big quantum measurement problem is this. If you look at the quantum postulates, then you will find two ways in which the wave function can evolve. It can evolve in time in this area by solving the Schrödinger equation. We all know that. But it can also, upon measurement, the wave function, you use the projection postulate to say, okay, the wave function collapses here into a new wave function, usually little delta spikes if you do this in position space. And that's another type of evolution. Now, that's not the problem. It's okay to have two types of evolution in a theory. What's the problem is we don't tell you when to use which. By what criteria do we know how to evolve the wave function? Why in this area didn't we use the projection postulate? How do we know what constitutes a measurement? So not saying that makes the theory ambiguous. Now, of course, by a lot of experience and by a lot of experiments, thousands and many thousands of experiments have been done, we kind of know in most cases, right? But that doesn't mean that the theory in that sense is clear on that issue. And that is one way of stating what the quantum measurement problem is. Now, people have worked on this for a long time. One thing that's been introduced is there's the famous work called Dara and Leggett and Zurek and many others, Zee, Joos. There's a lovely book by Maximilian Schlossauer that where you can read a lot of this and the references, which I would certainly recommend. What you start with, you have a quantum superposition. So right after the slit, the electron wave could be here or here. So we are in a Schrödinger cat type of superposition. Then you can get decoherence that eats the coherence, the capability of interference away when you would interact here with something that does that. That would lead here still to a distribution that cannot interfere, and it's called an improper mixture of quantum states. So even if you have decoherence that moves you towards more classical behavior, it still does not give the click pattern. So you could certainly, the quantum to classical transition, which is related to the quantum measurement problem, you could certainly cut into two steps. This step, well, that could be addressed maybe by adding nonlinear terms in the Schrödinger equation. Some people try that. And experiments are being designed and being tested to try to put bounds on such approaches. I wanted to first look at the decoherence in the experiments that we do. And that was proposed by Wojciech Zurek. And he said, you know, if you have here is your, say, diffraction or interferometer pattern, and you put that over a surface, then these electrons set up an image charge. The image charge consists of many electrons, and there's noise associated with it. So you have a back action back on the electron, and that can kill the capability of these two electrons to interfere. They can decohere the electron wave. And one way to think of it is it's not exactly right in our situation, but it's a straightforward idea that as soon as this electron would say excite a state here, if you could measure that state, you know where the electron is. So then you have localized it. And if you think back of the Bohr-Einstein discussion and Zurich's analysis, as soon as you know where the electron is, then of course you have which way information and you can interfere. And that's one way to try to understand why such a process with noise would eat coherence. Okay, and there's times, it takes a certain time. So you have to, when you design an experiment, to make sure that the flight time here would be sufficient to see the decoherence. Now here's an experiment. So first you have the gun, slit define beam, a non-fabricated grating. So instead of a double slit, the count rate is low. But if you have here many, many wires, then there's a freestanding grating with 50 nanometer wires, which was made at MIT. And so the first work we did on that was collaborative with the MIT group. And then you see then, when you are carefully coat this and make it, you can get the diffraction pattern. Then you put a surface here, just like Zurich suggested. And this work was published in 2018 and 2020. So this is more recent stuff. And then this idea that you have here, where are these two paths? Well, the two paths, if you take here two slits, then the electron can go to one of the two slits, interfere, and of course we blow up the diffraction pattern so we can see it. Now, this is without the surface. So here's a diffraction pattern. The zero order, the first order, second, third, etc. All you can see those orders. Then we introduce a wall. And when you introduce the wall, you see this happen. So first what you see is that electrons that were close to the wall at the bottom are pulled down. They're pulled down. Yeah, the image charge pulls them down. You can simulate this and it works quite nicely. You see another thing. You also see something that you would hope to see, that here the contrast is disappearing. You also note another thing, that here the beams are a little bit pointed towards each other. So you wonder, what is causing this? Right? Well, long story short, I mean, we've tried many ways to simulate this, but we succeeded in the end. What it happens is some of the electrons actually hit the surface. They leave behind a positive charge, and some of the electrons that make it, that contribute to the diffraction pattern, are disturbed by the local fields. Now, that is not decoherence. There's no quantum information stored in the surface. And we show that here. Here is the experiment, and here's a simulation. So here is without the walled experiment simulation, fit through it if one likes. But one can easily see that just with putting some potentials there, you get this loss of contrast, and this is called dephasing. So there's a difference between dephasing and decoherence. Dephasing is something that is in principle time reversible, where the entropy does not go up. And decoherence is something where the entropy goes up and there is which way information, and is fundamental and important to this classical to quantum transition. So our attempts here to make a decohering environment in the way that was proposed by England and Zurich here failed. Nevertheless, of course, you got to understand the detailed interaction between the wall and the electrons to be capable to get to the domain where you could get decoherence. Here's another one. We said, okay, you know, we note that in this decoherence time, if the resistivity of the material gets bigger, then the time it takes to decohere goes down. So you get more decoherence. In a little bit of time here, already something happens. So then I said, okay, let's take a different material. The other one was copper oxide. This is gallium arsenide. And with gallium arsenide, it has a band gap. So what you can do is you can put laser light on it and excite it. And you can go from conducting to non-conducting. So you can even control the resistivity and change by orders of magnitude. So I hope that was a good idea. And then we would hope to see this. So as we scan the laser over the surface, here's the surface, the electron beam is traveling into the board. Here's the diffraction pattern. We hope to see this, that the contrast would disappear, right, as the laser is there. So if you look here, right, but this is what happened. So it's very annoying. So the beam deflected, and it didn't matter if we took a laser that was sufficient energy to excite the band gap or not sufficient band gap with just a big effect, but the effect flipped over. So we conferred with some condensed matter experts, and they told us that there sometimes are trapping states and other things that affect us. So we built a model, and we can now predict what happens there. But sadly, that is again not decoherence. Turns out that it's actually pretty hard to get that decoherence, and it seems that we're starting to put bounds on the theories that predict it for this system. Now, so recently we actually did this. We said, okay, you know what? We're just going to take that beam, take two surfaces, slam it into the wall, let it come out. So the interaction must be super strong, and still we see a diffraction pattern. So then say, okay, gee, this may put serious bounds on theory. We're still in the process of working now. We're actually preparing a publication, and we're trying to make sure that we make appropriate claims. It's not obvious. But if there's no decoherence for the system, it leads to something else. It suddenly leads to an application, because then you could think of a fiber, but an optical fiber for electrons, and you start bending this, and you could maybe build very sensitive electron interferometers or do other, switching of electron waves, which would be highly exciting. So, at first I was very disappointed not to see decoherence. Now we haven't given up. We have even made smaller structures now that we're testing right now. But if we don't see it, then maybe we can do a very nice application. So with that, I want to thank you for your attention, and I hope that you saw something familiar. I hope you like that. And even if it was familiar, the double slit experiment, I hope that it's nice to know that there's still open questions associated with such a very basic, fundamental piece of physics. Okay, that was it.
Thank you, sir, for wonderful presentation.
Should I stop sharing, or would you like me to keep the slide open?
No, you can keep, because if we got some questions later, then you can easily show them. So
Okay.
we have got a few questions in inbox and in comments. So first, what are the example of uncertainty principle of angular momentum and angle? So we have an uncertainty principle on angular momentum and angle. So they want to know what are the example of this type of.
So let me see if I get this straight. The question is, can I talk about angular momentum in relation to this diffraction I was talking about? Let me go back. So let me go to, let's say, oops, that's a little too far perhaps. Let me talk about this, right?
Yeah.
Yeah. So, angular momentum is, of course, and momentum are both conserved, and those are very, very fundamental properties. So we always look for those. That's correct. So yes, to think about angular momentum makes a lot of sense. Angular momentum, if we look at this beam, of course, that depends on where do we pick the arm, right, of this R cross P. So what is R? Where's your origin from where we look at this? If I choose this in the center, then this would have no angular momentum. And if I draw this arrow back to the center, this also has no angular momentum. So I could say in this picture is designed in such a way that no angular momentum is transferred. You could, of course, also think of a plane wave here. Now, if the plane wave has an infinite extent, then it would even be harder to start talking about angular momentum. So usually in this thing, I have not seen a lot of discussion related to angular momentum. But by itself, if I want to know something about it, and I think of L equals R cross P, just classically, I would also love to know something about momentum transfer to be able to even construct maybe angular momentum transfer. Now, there's yet another thing I could say. I did a paper on that. So if you look at this thing, if you could transfer angular momentum, you could maybe control the spin of the electron. That would be very nice, because we don't know efficient electron Stern-Gerlach magnet for electrons exist, right? It was done with silver atoms, and for atoms and heavy objects it works beautifully, but for electrons it doesn't. So we don't have that tool to our capability. And of course I've published on that topic too, a couple of PRLs. Now the thing is, at some point I had the thought that maybe that's what you're thinking of. If in this light we control the angular momentum by going to circular polarization, then maybe we could transfer that to the electron and change it. Now, since there's only 2 electrons involved, an odd number can't do it. Sorry, an even number of photons can't do it. if you work out the angular momentum addition rules of quantum mechanics. But if you take an odd number, 3 photons, they can do it. The problem is a 3-photon process occurs at much higher intensity as compared to a 2-photon process. And thus you need to go to something like 10 to the 18th watts per square centimeter for that to happen. And then it's hard to keep it separated from other processes that may occur too, like spontaneous Compton scattering. And so the idea is lovely, and we published that in a PRA. But that was a theoretical paper. That was not an experimental paper. And I've been scared to try because it's so demanding experimentally. I think it can be done, but it's would require a fairly significant budget. And there's still other things I would like to pursue first. So yeah, angular momentum is an important thing to consider here.
Thank you, sir. So we have another question in comments. So is wave particle duality because of photon which are in form of quanta curved string? Photons carry only kinetic energy, then electrons carry only rotational energy. If yes, then photons are attached to electrons, so give velocity to electron as well as wave particle duality to electrons.
I'm sorry. I did not fully, the connection broke up a little bit. Let me see if I can repeat it. So is the question about if
So is wave particle duality because of photons which are in the form of quanta curved strings?
Okay, I think the question is about if photons carry momentum also and not just energy. Is that what it's about?
Yeah, maybe because of. Okay, I can show you the full question.
Yeah, that might be nice.
If you can stop share, then I can show you the question.
Okay.
Okay, I can add the question in the screen. Just look at the screen.
Yes.
Go
Okay, here we go. Is wave particle duality because of photons which are in the form of quanta curved strings? Now, photons carry only kinetic energy, then our electrons carry only RE. I don't know what RE is. If yes, then photons attached to electrons give velocity electron. Okay, I have never studied string theory, so I have no idea about that. What I do know is quantum optics, which is and some quantum electrodynamics. So photons to me are language that for me triggers the theory of quantum optics. And in quantum optics, you have say you could do it in the following way. You get a solution of wave equations where you replace the amplitude of the wave with creation and lowering operators. So you see a combination of creation and lowering operators and a wave such as, your usual cosine kx minus omega t, which means that the wave and particle duality is carried in that mathematical expression, which is a solution of wave equations, followed by second quantization. So that's sufficient. So photons is part of quantum optics, and the mathematical expressions carry the wave-particle duality. In the experiment, of course, we say the interference is kind of an expression of the wave nature, while the clicks that we see are kind of an expression of the particle behavior. That's often what is stated. Now, is that because of quantum curve string? I do not need to invoke let's say, a string theory to be capable to talk about photons and quantum optics. And that was the first part. The next part is about momentum. Yes, photons, of course, carry momentum, and photons carry only kinetic energy. Maybe that's not what it meant, because no, they do not just carry that. If you think, for instance, of solar sails, right, where people design solar sails in outer space and try to propel them, they could intercept electromagnetic radiation, and by photon pressure, radiation pressure, you could get some repulsion. So there's many examples, or you think of laser cooling. That's, of course, a famous example where also the momentum of photons is used. So yes, we know very well in many examples that photons carry momentum. And in this case, that is also used. Okay, maybe I at least address two parts of this question. It's cool.
Yeah, thank you, sir. This may be the last question. So, what is the Kapitza direct effect? I think you have already explained. So, could you repeat it, that effect?
Yeah, so the Kapitsa-Dirac effect is predicted in 1933, and what it is the diffraction of electrons from a standing wave of light. People realized that should be possible, and of course, in the time in 1933, there were no lasers. So Kapitsa-Dirac talked about the brightest light source that they knew that they could have in a lab, which is an arc lamp. So, and they calculated that the probability to have a chance of seeing this phenomenon is very small. And thus, in the 60s, when the laser became available, then suddenly people started trying. But there were multiple experiments that failed to do it. And then there was, for a period, people didn't try so much. And then I didn't know about all these things until later. And so then at some point, I worked out the parameters, and I had access to a laser that had the right parameters. And then there was another problem. Experimentally, what is very hard to do it is you have this bright electron beam with many, many electrons, and still only a few of them diffract. So you have to figure out a way to get rid of the center beam. And the way to do it is coincidence techniques to make sure that most of the time that when the laser pulse is not there, you don't accumulate data. And then for that 10 nanosecond, when the laser is there, then you accumulate data only. So the combination of coincidence technique and the right laser and the right collimation have allowed us to, observe this Kapitsa-Dirac effect.
Yeah, thank you, sir. So, thanks for your wonderful presentation and discussion session, sir. So, we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation.
Yeah, and it was my pleasure to be here. So if people still have questions, I do invite them to send, an email with a question, because
Yeah, so
I
I can
always.
add one question. So, I can add maybe.
Mhm.
Okay, this is not the exact question. This may be the just comment. So thanks,
Okay, good.
and hopefully in near future we'll arrange another webinar with some interesting topics with you if you have time. So
Yes.
thanks again, sir. Have a nice day.
Yeah, and thank you for the invitation, Pretam. It was a pleasure to
Yeah,
do.
it's my pleasure, sir. We're
Okay.
trying to do something, sir.
All right.
Bye.
Bye-bye.